A laptop GPU with only 8 GB of VRAM just ran a 35 billion parameter model at almost 40 tokens per second. And on a desktop with a single RTX 5090, a 284 billion parameter DeepSeek model reached more than 20 tokens per second. The models did not fit inside those graphics cards. They were far too large. The difference was a new local inference engine called FreeToken. In its creators' tests, FreeToken was up to twice as fast as the strongest competing local runtimes. In some workloads, the advantage was even larger. And the first community tests may be more impressive than the paper itself. So in this video, we'll look at how FreeToken works, how fast it really is, what hardware you need, and whether it could actually replace llama.cpp. Because the answer is more interesting than a simple benchmark win. FreeToken is not a new AI model. It is the software that runs a model on your hardware. That puts it in the same general category as llama.cpp or llama and K-transformers. But FreeToken is not trying to do everything they do. It was built around one difficult problem, running huge mixture of experts models when they cannot fit inside your GPU. That includes models like Qwen 3.635B, A3B, DeepSeek V4 Flash, Minimax M2.5, and GLM 5.2. FreeToken also supports GPT-OSS, Gemma 4, Muse Glimmer, and several other model families. The project is open source under the Apache 2.0 license. It can load supported Hugging Face checkpoints directly, and it provides both OpenAI compatible and Anthropic compatible APIs. That means a local model can connect to tools such as Codex, Claude Code, OpenCode, OpenClaw, and DeepSeek Harness without requiring a completely new workflow. There is even a command that configures and launches a supported coding agent against your local server, but none of that explains the surprising speeds. To understand those, we first need to look at the problem FreeToken is solving. A mixture of experts model does not use every parameter for every token. DeepSeek V4 Flash, for example, has 284 billion parameters in total, but only around 13 billion are active for each token. That makes the computation much easier than running a dense 284 billion parameter model. But the complete model still needs to be stored somewhere. If it is larger than your VRAM, the remaining weights have to stay in system RAM. The runtime must then decide which work happens on the GPU, which work happens on the CPU, and which weights need to move across PCIe. This is where a powerful GPU can end up waiting. The expert needed for the next token may be sitting in system RAM. Moving it to the GPU takes time. Running too much work on the CPU can also be slow, and a fixed split between the two may work well on one computer but badly on another. Your GPU, CPU, RAM speed, and PCIe connection all change the best answer. FreeToken treats those parts as one combined system instead of following the same static plan on every machine. The basic idea can be explained with 3 decisions. First, FreeToken remembers which experts are being used and keeps the most useful ones in VRAM. Think of this as a smart cache. If nearby tokens keep using similar experts, the runtime does not need to pull the same weights from system RAM again and again. In the researchers' RTX 5090 test, llama.cpp missed its expert cache far more often. FreeToken's cache adapted as the model generated each token, while llama.cpp used a more static split. Second, FreeToken overlaps work. While the GPU is processing the current layer, the runtime begins preparing the next one. The transfer does not disappear, but much of the waiting can be hidden behind work that is already happening. Third, FreeToken measures the computer it is running on. When an expert is not already in VRAM, the engine decides whether it is faster to move that expert to the GPU or calculate it directly on the CPU. That decision is based on the machine's actual memory and PCIe bandwidth. So a fast CPU with strong memory bandwidth can receive more work. A system with a faster PCIe connection can move more experts to the GPU. FreeToken can also change how much VRAM is used for expert caching and how much is reserved for the growing context without restarting the engine. These optimizations matter for normal prompts, but they become much more important when you use a local model as an agent. A simple token per second test usually sends one prompt and lets the model generate an answer. A coding agent behaves very differently. It reads files, calls tools, receives the result, changes its context, and sends another request. That context can grow to tens of thousands of tokens. When part of the conversation changes, it can reuse the unchanged section and process only the new part. This is one reason the researchers tested it with real agent workflows, instead of relying only on short synthetic prompts. Their tests included open code solving software issues, Claude Code using subagents, and an email and calendar agent completing a multi-turn task. Some sessions grew beyond 50,000 tokens. That brings us to the numbers. On an RTX 5090, FreeToken ran Qwen 3.635B, A3B at around 77 to 83 tokens per second across the tested workloads. With DeepSeek V4 Flash, it sustained around 22 to 25 tokens per second. Depending on the model and workload, that was roughly 1.5 to more than twice the speed of the strongest supported alternative. The bigger difference appeared when the agents repeatedly returned with long, changing contexts. FreeToken kept its generation speed relatively stable. Other engines slowed down more sharply or waited much longer before the first new token appeared. In the worst tested turn, FreeToken started generating in under 44 seconds. Every competing engine crossed 150 seconds somewhere in the tests. The longest stalls reached several minutes. For an agent, that is not merely an annoying benchmark number. A long enough delay can cause the client to assume the local server has failed. The results also covered less extreme hardware. Take an RTX 4060 laptop with only 8 GB of VRAM and 32 GB of system memory. FreeToken ran an official 4-bit version of Qwen 3.635B, A3B on it at 39.3 tokens per second. The model did not fit in 8 GB of VRAM. System RAM held the remaining weights. That distinction is important. On a workstation with 196 GB RTX Pro 6000, FreeToken ran the 753 billion parameter GLM52 at nearly 15 tokens per second. In the same comparison, llama.cpp reached a little over 7. These are impressive results. But they come from the FreeToken paper written by the people who built the system. Independent tests matter, and we now have at least one early result. One local Llama user tested FreeToken with an RTX 5080, 64 GB of system memory, and a Ryzen 9 9950X3D. Qwen 3.635B A3B did not fit inside the GPU's 16 GB of VRAM. Even so, the user reported around 100 tokens per second, with one example reaching roughly 110. That is a reported community result, not a controlled independent benchmark. Other users also pointed out that a smaller quantized model can already run extremely fast if it fits completely in VRAM. And that is exactly where the comparison can become misleading. FreeToken is most interesting when the model does not fit. If your chosen quant already fits completely on your GPU, moving weights between RAM and VRAM is no longer the main problem. llama.cpp can still be extremely fast in that situation. If you try FreeToken, share your GPU, system RAM, model, and speed in the comments. Results from normal gaming PCs will teach us more than one benchmark table. Possibly, but the current requirements are much narrower than llama.cpp. The documented command line installation requires Linux on an x86-64 computer, an NVIDIA GPU, CUDA 13, and a recent driver. The project currently highlights RTX 30, 40, and 50 series cards. FreeToken also advertises a desktop application for Windows and Linux, but the core documentation and accelerated setup are still heavily focused on Linux and NVIDIA. There is no comparable Apple Silicon path right now. It is not a universal CPU runner, and it does not have llama.cpp's enormous GGUF ecosystem. Most supported checkpoints use Hugging Face safe tensors, although Gemma 4 has native GGUF support. You also need enough system RAM to hold the part of the model that does not fit in VRAM. An 8 GB GPU does not magically make a 35 billion parameter model occupy only 8 GB. The laptop in the paper also had 32 GB of system memory and used an official low-precision checkpoint. For a model as large as DeepSeek V4 Flash, the system requirements rise dramatically. A 32 GB GPU may do the active computation, but the complete checkpoint still needs much more memory elsewhere in the computer. So FreeToken uses the hardware you already have more efficiently. It does not remove the model's real storage and memory requirements. Not for everyone, and not yet. llama.cpp supports an enormous range of models and hardware. It runs on Windows, Linux, macOS, CPUs, NVIDIA GPUs, AMD GPUs, Apple Silicon, and even small devices. It is mature, widely tested, and sits underneath many of the local AI tools people already use. FreeToken is younger and much more specialized, but specialization is also its advantage. If you have an NVIDIA GPU, enough system RAM, and a large MoE model that cannot fit in VRAM, FreeToken may already be the more interesting engine. It was designed around exactly that situation, especially when the model is powering a long-running coding or tool-calling agent. This is not llama.cpp losing at its own entire game. It is a new engine finding one increasingly important workload where the old general solution may no longer be the fastest. And as open models grow larger while activating fewer parameters per token, that workload could become much more common. FreeToken does not turn an 8GB graphics card into a data center GPU. The full model still has to live in system memory, and platform support is limited, but it appears to make much better use of the complete computer. The official tests show large MoE models running between 30% and more than twice as fast as competing edge runtimes. The first community result suggests the real-world potential could be just as interesting. So no, FreeToken is not the new llama.cpp for every device, but for models that are far larger than your VRAM, it may be the first serious sign that local frontier inference is becoming a software problem, not only a hardware problem. Subscribe if you want to see a complete FreeToken setup guide and real comparisons against llama.cpp as more community results arrive.